Well, welcome again to our journey into number theory, and this is the second section of chapter 1. And chapter 1, remember, is just a bit of a quick tour de force through classical number theory, and many of the proofs I'll leave you to have a look at from other standard books. So we're talking a little bit about solutions of something like x squared is congruent to minus 1. So when is minus 1 a square mod p? P is prime, and we saw that was true if p was a 1 mod 4 prime. And so it raises the question, well, what numbers are squares modulo p? And that's a whole topic in itself. We're going to have a look at. This is called quadratic residues. So quadratic residues are simply squares mod p. So if x squared is congruent to a mod p has solution, that is if a is a square in zp and a is not naught, then we say that a is a quadratic residue modulo p, or a QR for short. Otherwise, if it's not a square, it's called a quadratic non-residue, which is abbreviated to QNR. For example, if we look at U11, which consists all the numbers that, I should say in U11, which is all the numbers from 1 up to 10, because that is prime, then these are the squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 5 mod 11, and 5 squared is 3 mod 11. So they are the squares, and that means the remaining numbers, of which here, these are the non-residues, or the quadratic non-residues, the non-squares. Now it's almost obvious that exactly half of the numbers in UP are going to be quadratic residues. However, I wanted to give the proof is almost obvious, but I'm going to give a slightly different proof that gives a little bit of insight into how we can find the squares and connect them back with the primitive roots. And here's a little proof of this here. So this is a proof of theorem 1.2. So let G be a primitive root modulo P. We know that if P is prime, then ZP has a primitive root. I call it G. And we can get the squares really easily modulo P by simply taking the even powers of the primitive root. So these are obviously squares, and moreover they're all distinct mod P. And indeed there are P minus 1 over 2 of them. On the other hand, if I have an odd power of the primitive root, let me suppose that that is a square for some x, perhaps I should say for some x in ZP, then I can raise both sides of this to the power p minus 1 over 2. So I just do that. Now that gives me x to the p minus 1, but by Fermat's little theorem, x to the p minus 1 is just 1 mod p. On the other hand, if I take this quantity here, I can interchange the indices just by using the index laws, and I obtain this. And we know that g to the p minus 1 over 2, g is a primitive root, then this has to be minus 1, and minus 1 to an odd power gives me minus 1, and that's a contradiction. We get 1 on one side and minus 1 the other, and so we have a contradiction. So that tells us that the even powers of the primitive root, the p minus 1 over 2 even powers are squares, and the p minus 1 over 2 odd powers are not squares. And so that's a nice little fact, just proving that result that was otherwise fairly obvious anyway. What we're looking for is we want a simple test. Is there a simple test to determine whether a given number a is a non-zero square in ZP? For example, if I give you this modulus, 12, 7, 13, is 3127 a square in here? Well, I don't know, because we haven't got enough tools to see that at the moment. I certainly don't want to take all the numbers in here and start squaring them and then read them modulo this, and moreover trying to get a primitive element here and then taking all its even powers is not going to be a good way to check this. So we'd like some sort of criterion, some method of checking what number is a square in this ring. So to do that, we have a lovely thing called Euler's criterion. And in fact, it is a special case of that theorem 1.1, the proof of that, which I'll leave you to go back and check and see if you can give a proof of that. So it says if P is an odd prime and P doesn't divide A, then x squared is congruent to A mod P is solvable, that is, A is a square, if and only if A to the P minus 1 over 2 is congruent to 1 mod P. That means that A is a non-square or a non-residue, quadratic non-residue, if A to the P minus 1 over 2 is minus 1 mod P. So at least at the moment, this gives us some kind of criterion for checking when a number is a square. And just as a little example, I've kept the numbers small here, but is 3 a square modulo 23? And let's just do a little example here to have a look at that. So what we do is, to use Euler's criterion, we need P minus 1 over 2, which happens here to be 11. And to check whether 3 is a square, I just have to check 3 to the 11. I have to modulo 23. Well, you can just fiddle around. I just fiddled around a bit here. I said 3 cubed is 27, which turns out to be 4 modulo 21, because this is 3 cubed is 27, which is 4 more than 22, which is 0. So I can square both sides. 4 squared is 16, and 16 is minus 7 mod 11. And I can multiply these together and then simplify mod 23. I get minus 5, and then I can multiply by 3 a couple of times and get up to here. I get minus 45, and minus 45 turns out to be 1 mod 11. Sorry, mod 23, I should say. So that's mod 23, because it's this is 46 minus 45 is 1. So Euler's criterion then says that 3 to the 23 minus 1 over 2 gives me 1 mod 23, so 3 is a quadratic residue modulo 23, and in fact, you could play around a little bit, you'll discover that 7 squared is 3 modulo 23. So that in fact is the number which when squared gives me 3. So 3 is a square modulo 23. So Euler's criterion then is very useful. It's a very useful theoretic tool, but for large moduli it is not very practical, because even with that simple example we had to do a reasonable amount of calculation to solve that. Now, we're going to introduce then this idea of Legendre's symbol, and this is a lovely, lovely example of where notation in mathematics can really, good notation can get you a long way. And so this is this lovely Legendre symbol, and it's written as A over P in round brackets. So P is our prime, A is some number in ZP, some non-zero number, where A and P are relatively prime. And P, by the way, will be, whenever I write P, it's going to be a prime unless I tell you otherwise here. I won't always say P is prime, but you can assume from now on it is, unless I say otherwise. So we say that A over P is 1 if A is a square mod P, and this symbol takes the value minus 1 if A is a non-square mod P. This is an interesting example. We're going to generalize this a lot later on when we get to characters. This is going to be an example of a character of order 2. It's a these are the 2 square roots of 1. And this is going to be called a character later on of order 2. Here at the moment we're just going to say that if A is a square, then that symbol takes the value 1. If A is not a square, it takes the value minus 1. We can now write Euler's theorem as A over P is congruent to A to the P minus 1 over 2 mod P. Because if A is a square, this is 1, and that's what makes this work. And if a is not a square, this is minus 1, which is what we've written there. A couple of trivial cases here. If for AP relatively prime, 1 over p, of course, is 1, because 1 is a square, and a squared over p for any a is also 1, because a squared is obviously a square. And we've also seen that if p is 1 mod 4, then we've seen that you can take the square root of minus 1. There is a number whose square is minus 1 mod p, and so minus 1 over p is 1. Now, theorem 1.2, we saw that half the numbers in ZP are squares and half the numbers are not squares. So half the numbers are going to give me a Legendre value of 1, and the other half are going to give me minus 1, and if I add them all up, you must get 0. So that's immediate consequence of that there. Now, little theorem here, which is very simple to prove, but is quite useful. This says if a and b are the same modulo p, then their Legendre symbols are the same. If a and b are congruent mod p, then their Legendre symbols are the same. So you can replace a with b, which is congruent to it mod p. That's a very useful little fact. The second one is the Legendre symbol splits. In fact, there's no conditions on a and b here. They don't have to be relatively prime. This function, in fact, is completely multiplicative. This always splits in 2, and you don't care whether the a and b are relatively prime or not. Well, we better get a little bit of practice at calculating with these Legendre symbols, so we'll calculate a number of these little ones here. So let me just pop this in here. Here are some examples of calculating these Legendre symbols. So 19 over 5. So what I first do is I've got 19, I'm working modulo 5, so I replace this with something that is congruent to it, modulo 5, and this is just going to be the same as 4, because 5 3 is 15 plus 4 is 20, so I can replace this with something congruent to it, and now I'm finished, because 4 is obviously a square, it's 2 squared. So the value of the Legendre symbol is 1. So 19 is a square modulo 5. 47 on 17, well, again, I can replace this, I can subtract off a few multiples of 17, and then I land at minus 4. Okay, so I've just subtracted off 17 a few times, in fact 3 times, and I get minus 4. Now, minus 4 is minus 1 over 4. I can split this into minus 1 over 17 and 4 over 17, and 4 over 17 is a square, so that's the Legendre symbol is just 1, and I'm just left with minus 1 on 17. And 17 is congruent to, so just note here that 17 is congruent to 1 modulo 4, and we know that primes that are 1 mod 4, minus 1 is a square, and so the Legendre symbol there is 1. 5 on 7, you can do these in many different ways. I invite you to play with these and do various different ways of doing this. You'll get the same answer, but just do it in different ways. 5 on 17, I'm going to subtract 17, I get minus 12. I take the minus out, and then I've got 4 3s are 12. I can take a 4 out of there. 4 on 17, 4 is a square, so 4 on 17 is 1. So I get a minus 1, and I've got a 3. Now once again, we know that 17 is a 1 mod 4 prime, so that's 1. So that gives me 3 on 17. And at this stage, you can fiddle around with it a bit more, but what I'm going to do now is I'm going to use Euler's criterion. And so 17 minus 1 over 2 is 8. And so this is congruent to 3 to the 8 modulo 17. And then you can just, with a bit of fiddling around, you can start cubing this and so on until you get up to 3 to the 8 and you discover it's minus 1. And that means that 5 is not a square modulo 17. 5 is not a square modulo 17. Now you can see, even with this last example, you've got to do a fair bit of calculation and to get yourself down to a point where you can use Euler, and even then you're going to have a bit of work to do. And you can see that if these numbers were very large, then this sort of technique can be very, very slow. So we really need something a little bit better, and we're coming to that soon. Now, Gauss discovered a wonderful thing called the reciprocity theorem that we will get to probably in the next video. But as a stepping stone to that, we need what is known as Gauss's lemma. Gauss, in fact, gave lots of proofs of this reciprocity theorem we're going to get to. However, it was Eisenstein who gave what Gauss regarded as the best proof of it, and most of the proofs of the reciprocity theorem all depend on Gauss's lemma, as does Eisenstein's one. There is another way of getting to it without using Gauss's lemma, by using characters, but we probably won't be doing that in these lectures. So the point is, there are still computational difficulties. For example, how on earth do we find this? The numbers are very big. So the key to evaluating Legendre symbols is Gauss's famous reciprocity law that we'll look at later. Gauss gave a number of proofs, all of them with one exception relied on the following, I think, rather strange result. It's rather odd when you first look at it. It's known as Gauss's lemma. As I mentioned, there is a wonderful two-line proof of this, but it requires characters and Gauss sums, which we won't be looking at. So this is what it does. You start off with a p as an odd prime and a and p relatively prime, and you consider this set S. So you take your a and you double it, triple it, up to a half p minus 1 times a. You now take these numbers and you reduce them modulo p. You reduce these modulo p. You then let k be the number of elements in this reduced set S in the reduced set S that are greater than p minus 1 over 2. So you write those down. You count the number that are greater than p minus 1 over 2, you call that number k, and then almost miraculously the Legendre symbol a over p is minus 1 to the power k. It's quite a strange result, and I'm going to go through the proof of this. Is worth seeing Gauss's lemma. Okay, so here's how it works. Proof of Gauss's lemma. So remember, what we did was we started off with this set S, which were the multiples of a 2a up to half p minus 1 times a, and we observed that the elements of S are all distinct. Now, of course, what we have to do in Gauss's lemma, we're going to read this modulo p, because these numbers will be bigger than p in general, and you may have to reduce them down so that we get them in that set. So we let S dashed be the set A1 up to AK. These are the elements of S reduced, I suppose I should say here. So you take these and reduce them, reduced, which are bigger than p minus 1 over 2. And of course our aim is to prove that the Legendre symbol a over p is minus 1 to this mysterious k. Okay, so what I'm going to do is I'm going to take p minus each one of these. So these numbers are all bigger than p minus 1 over 2. So I take p minus all of these numbers, and that means these numbers are going to be less than or equal to p minus 1 over 2. And then I take the ones in here that are the remaining elements. I take these ones that are the remaining elements of S. That is, these are the ones that were in S reduced that were less or equal to P minus 1 over 2. Okay, so A1 up to AK are the numbers bigger than P minus 1 over 2. AK plus 1 up to this in some order are the remaining elements that are also, that are less or equal to P minus 1 over 2. And then I take P minus each of these, and so this list is also all the ones that are less than P minus 1 over 2. And these elements you need to check, these are all distinct. And if they're all distinct, then these numbers here listed are all the numbers that are less or equal to P minus 1 over 2. I.e., these are precisely the numbers from 1 up to P minus 1 over 2, but in some order. Finally, then, I'm going to multiply everything together. So I'm going to multiply all the numbers in this list together, and that gets me this. And these numbers are supposed to be these numbers in some order. So when I multiply them, the product of all these has to equal the product of all of these numbers, modulo P. Okay, well that means then that I can simplify this a little bit. If I look at this modulo P is A1 with a minus sign, this modulo P is A2 with a minus sign. So I'm just going to get A1 up to P minus 1 over 2. But I'm going to pick up a pile of minus signs and I'm going to get K of them. And this product still is congruent to the product 1 up to P minus 1 over 2 mod P. Now, of course, these numbers then, these numbers here, these are all the numbers back in the original set S. And the elements of S, remember, were just A times 2A and so on. And so I'm going to get a whole pile of A's, and then I'm going to get the numbers 1, 2 up to a half P minus 1. And that's what I've done here. So I'm going to get P minus 1 over 2 A's, and I'm going to get, I've still got a minus 1 K, and I get the numbers from 1 up to P minus 1 over 2. Now, these numbers all have inverses modulo P, so I can cancel out both sides of this. And I just get A to the P minus 1 times minus 1 to the K is 1. Multiply both sides by minus 1 to the K gives me that. And then Euler now, beautifully, tells me that A to the P minus 1 is over 2 is just my Legendre symbol. And so that is minus 1 to this rather mysterious K. And so that is a little proof of Gauss's lemma. Now I would suggest a nice exercise would be to actually calculate by hand one of these Legendre symbols using Gauss's lemma. Perhaps pick one of the ones that we've already pre-calculated. And in fact I'm going to in fact do one of those. I'm going to do 5 on 13 just to finish off with, and we'll have a look at calculating. So there's the proof of Gauss's lemma. We're going to use Gauss's lemma to find 5 over 13. I kept the numbers small here. So here we are, this is what we do. We're going to evaluate 5 on 13 Legendre symbols. So P is 13. So P minus 1 over 2 is 6. So I take the multiples of 5 up to 5 times 6. So that's 5, 2 lots of 5, 3 lots of 5, 4 lots of 5, 5 lots of 5, up to 6 lots of 5. That was our S. And now we reduce this modulo 13. So 5 is 5, 10 is 10, 15 is 2 mod 13, 20 is 7 mod 13, 25 is 12 mod 13, 30 is 4 mod 13. Now you look for the numbers in the set that are bigger than P minus 1 over 2. P minus 1 over 2 was 6. So that number's bigger than 6, that number's bigger than 6, that number's bigger than 6. And that means my k then is 3. It's the number in this set that's bigger than p minus 1 over 2. And finally then, Gauss's lemma says that 5 on 13 is just minus 1 cubed, and minus 1 cubed is minus 1, which tells me that 5 is not a square modulo 13. Well, this is still a rather odd thing, this Gauss's lemma. I see it more as a stepping stone rather than a major result in itself, and we're going to use it next time to work out the Legendre symbol for 2 over p, for general prime p, and then we'll move on and have a look at Gauss's reciprocity theorem.